Kia ora all. Here I am with the TGC Derived Grade Exam 2024, Level 3 Chem. This is the Aqueous paper, and this is going to be question 1, which actually was done really well. So good job all you guys who pushed through and did this tricky paper. So we've got this information here that nitrous acid is a weak acid. Probably didn't need to be told that, because if you get a Ka, it tells you that it's weak. So we have to determine its concentration if we know the pH. So we should know that to determine the pH of a weak acid, we need to write an equilibrium for the weak acid dissociation. So that is going to be NO2 minus and H3O plus, and then we need to write a Ka expression, which is our products over our reactants. Okay, so the question asks us to find the concentration of this. We have the Ka given to us, and we have a pH, therefore we have the H3O plus, and one of our assumptions is that these two are equal, because this is a pure dissociation, not a mixture or anything like that. So we are going to put the Ka in here, 7.08 times 10 to the negative 4, and that's going to be 10 to the power of negative 2.08 squared over x. And when I carry on and do that calculation, I am going to end up with x equaling, and I need to give this 3 significant figures, and it is going to be 0.0977 moles per litre. This was a merit question. You didn't get marks off for not doing the significant figures, but actually it's just silly if you don't keep doing 3 sig figs. But well done for those who got that merit there. This one, some of you found a bit tricky, but it actually was linked to the previous question. So you had to know about sodium nitrite. And when you first look at it, you think, I don't know about sodium nitrite. No, that's a very unusual compound. And you're right, it is, except that up here, we wrote an equation with this nitrite ion here. So this is a weak acid, therefore this is its conjugate base, and that is where you needed to start. So NaNO3 is therefore a salt, it's ionic, sorry, NaNO2. It is a basic salt, and we needed to start there. And even before we start circling, let's get our equations done, because that's going to help us with what we need to do. So we should know, once we've established that it's a salt, ionic, so we've got a positive sodium ion and a negative nitrite ion. So it's going to fully dissociate to make some ions, Na plus and NO2 minus. I'm going to put my water up there. And then I know it's a base, because up here I figured that out. That was a weak acid. That is its conjugate base. So my second equation down here is going to be the reaction of that with water. I know it's going to be weak, and I know it's going to accept a proton to go back to HNO2 plus OH minus. Once I have these two here, I can then have my answer. So my answer is it a good or a poor conductor? It is good. That is related to my first equation. What is its pH? Okay, I can cross out all the acidic. It's not neutral. It's one of the two bases. And I'm just going to go ahead and say it's a weak base. So it's more likely to be 9 than it is 13. And now we have to explain this. So number 1, it's a good conductor. So I'm going to link it to my equations. So NaNO2 fully dissociates in water to form a high concentration of ions, in this case Na plus and NO2 minus, to conduct electricity. Let's get that defined. Moving charged particles are needed, and with a high concentration of ions from the full dissociation shown above, NaNO2 is a good conductor. Right, to talk about the pH, pH equals negative log of H3O plus. You don't really need to write that, but I'm just going to write it all in. The higher the concentration of H3O plus, the lower the pH. Right, so I'm now going to refer to this second equation here. The NO2 minus ions react with water to a low extent. You can say partial dissociation, but for a Bronsted-Lowry base, I tend to like saying except few protons or equilibrium lies to the left. So I'm going to put that there. Equilibrium lies to the left. Partial reaction. Okay, a low concentration of OH minus is therefore formed, but the concentration of OH minus is greater than the H3O plus, therefore the pH is greater than 7. So I do need to put that in, and I need to say why it's basic, and then I need to say why it's 9 and not 13, as the equilibrium lies to the left. The concentration of OH is not as high as a full dissociation. Therefore, the pH equals 9. Right, so that one there is kind of a level 2 question, but the tricky bit was this bit at the start and linking it right back to the first part of the first question. Okay, then we get on to buffers. So a buffer solution can be made by adding some, we're still using the same compounds here. So we've got NO2 minus and HNO2. We've got a pKa. This is a state, and all of us did that, 2.15 to 4.15 for an achieved. And we've got two buffers. Now, some of you really need to read the question a bit carefully. We've got buffer A, which has a pH of 2.7, and buffer B, which has a pH of 3.5. Compare the effectiveness of both of these buffer solutions towards added acids and base, and we must use equations. So let's just start with the equations. So we've got NO2 minus, which is our weak conjugate base, reacting with our acids. And that would make HNO2 plus H2O. And then we've got our weak acid part of our buffer, which would react with any added OH minus to give us the conjugate base plus H2O. So those are our two buffer. So we could say, doesn't really ask what a buffer does, but a buffer, we'll just say it anyway, maintains a constant pH as it is composed of a weak acid conjugate base pair. Okay, both of these buffers are effective. Only one or two of you recognise this, as their pH is within the effective range. So I guess, why did they ask you this question here? And it is possible to link it because, look, 2.7 is within that, 3.5 is within that range. So both of these buffers are effective as their pH is within the effective range, 2.15 to 4.15. However, buffer A, pH is 2.7, which is less than the pKa of 3.15. Therefore, in buffer A, the concentration of the weak acid is greater than the concentration of the conjugate base, and therefore this buffer is more effective at removing added base. It's got more acid in it, so OH minus. C equation, and I'm going to number these, 2. Okay, and the other buffer, buffer B I named, I could call it has got a pH of 3.5, which is greater than the pKa of 3.15. So you did have to make these numbers a bit more useful than just numbers. So that's a pKa, that's a pH. So therefore, if we've got a higher pH, the concentration of the conjugate base must be greater than the concentration of the acid, and therefore buffer B is better at buffering against, bad spelling, sorry, added acid or H3O+. Okay, so I've got equations and they are relevant equations. I've said they're both effective, and I've related the pH to the pKa to say why they are more effective against added acid or base. And finally, we get a buffer calculation. So there are two ways to do this buffer calculation, and most of you did choose the way I taught you, which is always good, I reckon. And what we need to do is write a Ka expression for the weak acid. So the weak acid's nitrous acid again. So we've already done it. So usually I would suggest that you write the equation first. But actually I'm going to just go back and copy this and just check that I've got it right. So I've got Ka equals NO2 minus H3O plus over HNO2. Okay, so I have to calculate the mass of, so it's this thing here I'm calculating. I've got a volume, and I've got a concentration of this thing here, and I've got a pH, which will give me the H3O plus, and I've got a Ka, which goes in there. So at the moment I've got that number, I've got that number, and I've got that number. So I'm going to rearrange and solve for NO2 minus. So that's my first job. So I'm going to go, the Ka is 7.08 times 10 to the negative 4. That equals X times 10 to the negative 2.74, which is my H3O plus concentration, and my HNO2 is 0.125 moles per litre. So if I rearrange that and tap away on my calculator carefully and solve for X, I am going to get the concentration of NO2 minus is 0.0486 moles per litre. And it would be really good if we could have a few more units in there. And I think, even though you might think I'm being a bit punitive and saying put your units in, actually it's so that you know what numbers you're dealing with and you don't put them in the wrong place in your next step, which has happened quite a lot. So that's our concentration of NO2 minus. I now want to know the number of moles of this, and so I've got 150 mils. So N equals C times V, which equals 0.0486 times 0.15 litres, and that is going to be 7.29 times 10 to the minus 3 moles. That number of moles of NO2 minus is the same as the number of moles of NaNO2 because they dissociate in a 1-to-1 mole ratio. So my mass is therefore going to equal N times M, which is going to be 7.29 times 10 to the minus 3 moles from the previous part times the molar mass, which is 69.0, which equals 0.503 grams to 3 significant figures. So many of you did a good job there, and most of you who made an error did one silly thing somewhere, and often it was to forget this step actually. But you had to get a pretty good effort to get a merit here as well. You couldn't have more than one error to get a merit in this question. And that is the end of question 1.